So, welcome back, and we learned yesterday about gravitation, about the beautiful inverse square law that was proposed by Newton, and the universal gravitational constant, etc. And in doing so, we arrived at an equation F is equal to minus g m1 m2 upon r cube vector r. Okay, so this relation was obtained by us. This could also be written as F is equal to minus g capital m1 m2 upon r square into r cap. So this is with you. We talked about that, and we talked about a system of two masses m1 and m2 separated by a distance r from each other, and wherein we have two forces F12 force on body 1 due to body 2, and an equal and opposite force conforming to the third law F21 shown here in the opposite direction. And from third law we find that F12 is equal to minus F21, so we can write that F12 plus F21 is equal to 0. Okay, it's not very difficult, we have already done that. So if I say that the magnitude of these two forces F12 and F21 is equal to F, then we can state Newton's law of universal gravitation as F is proportional to m1, F is proportional to m2, and F is proportional to 1 upon r square. Okay, so that if we take all these things together for mathematical consistency, I can write that F is proportional to m1 into m2 into 1 upon r square. And then we get the constant of the proportionality of the system, and that turns out to be capital G, and of course capital G does not depend upon m1, does not depend upon m2, does not depend upon r, the shape, size or whatever of the bodies under consideration. So we have a scalar relation F is equal to capital G m1 m2 upon r square. When need be, we can talk about the vector relationship, and in the vector relationship, do remember that this minus sign indicates that the force is attractive in nature. Okay, attractive in nature. Now let us state that for the earth I can write m1 as equal to me, small r is equal to re, the radius of the earth, m2 is equal to small m, which is located on or near close to its surface. Okay, and in that case I can write this equation F is equal to capital G me upon re square multiplied by m. And because capital G is a constant, me is a constant, re square is also a constant, the whole thing becomes a constant. And for this constant I can write small g. So this is now again from Newton's second law type of an equation we get that the force is equal to G multiplied by M, like M multiplied by small g or M multiplied by the acceleration A. So naturally, if we compare here, then we find that the small g is equal to capital G me upon RE square, which we call acceleration due to gravity. Okay. Now, before I proceed further, I will talk to you about gravitational field. The gravitational field, I am writing field in analogy with the, I just define it. Suddenly, that capital EG, the vector is equal to vector F divided by M. What does that mean? That means that the force on this body of mass M, which can be varied, this force is directly proportional to this mass M. So this gives Fe is equal to a constant times in M. Of course, I can say that there is a relation like this. This is Fe, F and M. So this goes like this. Okay. But for the system as it is, the slope of this graph gives us the value of Eg, which is nothing else than the small g, because I am just taking the scalar values, but we define here and we find it like this. So F is equal to Eg into M. Here Eg is the constant of the system. I am sorry, I insist that it is the constant of the system. What is the system? The system is a mass. For example, in the Earth system it is Me, in the other system it is M1, whatever mass you want to take, and this is a test mass, kind of a test mass. And one of the things that we obtain for Eg, the constant of the system, is, and again I am writing the scalar form, and I am writing for you that Eg, this is a very important thing, for the gravitational field as also for the electric field and magnetic field, etc. Okay. So here this is not a function of the mass M. It is not a function of mass M. Then the question is, what is it a function of? Eg is a function of the system, the defined things of the system. That is, there is a mass, for example, here, and we can keep it like that. You can see that if the value of R is reduced, if the value of R is reduced, keeping the value of M1 and M2 the same, then what we find that the force, the magnitude of the force F, which is equal to F12 magnitude is equal to F21 magnitude. This turns out to be equal to. So we had, I was telling you that this Eg, or the field that we have defined here, the constant of the system, it does not depend upon the mass M that we have taken, but it is rather a function of the system. It depends upon the system, the location of the point, etc. And the system is, I also showed you that here the slope is equal to delta F upon delta M. Okay, the slope, we can have this like this, this is delta f upon delta m. This is all I have told you in the beginning for the proportionality systems. Okay. Now there is a very beautiful thing about this concept of the field. About the field I have to tell you something. I have to share it with you because many a teacher, many a author of books, he describes the field as the area around a point where the effect of a mass or a charge can be obtained. So this field is actually the effect. And in a nutshell, because this is not the time to tell you about the field in general, so what I have just drawn is a point mass m, and I have shown you 8 lines which are progressing towards this mass m. They are lines in space. And of course, this is actually what I should have drawn here is a spherical surface, but I have just sliced this spherical surface and got a circle over there. So there are many field lines which are coming from all sides, and they are culminating in mass point here at M. These are called field lines. These are called field lines of gravitation. You can see that the distance between this and this, these two close by lines, is larger than when we come nearer, closer, and closer, and closer. And if we go out further, then the separation, and of course the angle between these two lines remains the same, unchanged. So, for defining the, for example, the electric field, if I define here at this point, one of the points, just say P, and I describe you the electric field, magnetic field, due to this mass M, because it is attractive in nature. So the lines of field, they point towards this mass M, and the value of the field over here, it does not depend upon the mass that we take over there. This is a kind of a test mass. So what is the field? The field is a beautiful concept in any discipline, gravitational, electric, magnetic, and many other things, that it is a measure of. The thing is, if there were a mass small m over here, then this small m mass will feel a force in this direction. Okay, so it is just in order to explain to you that we take the small m, okay, and I did show that if the value of that small m is increased, then of course the force due to this mass on this mass m will increase, but E will remain unchanged. Okay, so lines of field, if they are and now what I can tell you is something very interesting, that suppose there is a mass, and suppose there is a mass and it has many forces acting on it, okay, we can have several other masses, we can take them individually, we can have several vectors like this, and then ultimately what is going to happen, we can have this vector plus this vector plus this vector plus this vector plus that vector plus that vector, etc. And finally I can obtain, at this point I can obtain a force in this direction. Force in this direction. So this force is due to what? It is not due to this mass. This force is because of the distribution of masses at different locations, near or far. Okay, so it culminates into a force like this, and I can write that if there is a mass m over here, the mass m multiplied by E gives the value of the field. So field is a concept, a beautiful concept, a non-measurable concept. Force is measurable, field is not. Okay, so this is the same thing as what I will talk to you when I am talking about the electric field. Similarly, this field exists over here. So I want you to bear in mind that the Eg is equal to G, and if you take G as a vector, small g as a vector, then this electric field is also, it's because of E that I call it electric field. No, the field is equal to G. So you have to bear in mind, you have to go through the lecture again to understand what is the field value and how it exists. So I talk more about it. We take a few examples of involving the calculations, and I want to transfer to you some information about the various masses and the distance. And this is the Earth to Moon system. Okay. So the question is, we give you the mass of the Earth as 6 into 10 to the power 24 kilogram, mass of the Moon 7.4 into 10 to the power 22 kilograms. The Earth to Moon, the distance between the centers of the two objects, which I am taking as r is equal to 3.84 into 10 to the power of 8 meters. Sometimes it is given in kilometers, so be careful about that. Capital G is like that, the value I am giving to you, so that it comes to your brains time and again. Now the question is very simple. Calculate F, the force exerted by Earth on the Moon, and equivalently by the Moon on the Earth. The two forces are equal and opposite. F12 is equal to minus F21, and we use the formula. We'll write in the first instance the formula in the form that we remember: capital G m1 m2 upon r square. And so I put the values and obtain the result, which is substantial 20.2 into 10 to the power of 19 newtons. Why I take this example is that there are 5 items, 1, 2, 3, 4, 5. If any 4 of these items are given to us, then we can calculate the other item. For example, we can calculate, capital G. Let me write. What will be the formula derived from this formula will be equal to Fr square m1 m2, and we can calculate and find out the value. We can calculate m1, for example, m1, and this will be given as F into r square. Other things are known to us. Fr square divided by capital G m2, and we can also calculate m2 here by the same kind of formula and writing m1 here. Okay. We can also calculate the value of R, and the value of R, for that we write that R is equal to, other things are known to us. R will be equal to how much? R will be equal to capital G upon F, capital G M1 M2 upon F. These things are known to us, and we just have to substitute these values, and we find the distance between the moon and the earth. We calculate using this formula. Okay, so from one formula is directly written. I have calculated the value of F. I have got 1, 2, 3, 4 other formulae which are derived from that. So this is how the things are done. One thing I want to share with you, that F was proportional to 1 upon R square. So the graph between F and 1 upon R square, I'll just stop momentarily. R square, 1 upon R square. What will be it? What shape it will have? Think. The shape will be something like this. And the slope in that case will be equal to, slope will be equal to, with the help of this slope, is equal to capital G M1 M2. Because here force is directly proportional to 1 upon R square. So it is Y is proportional to X, and Y is proportional to X is a linear curve. But if I take this as R in meters and F in Newton, then the graph will look something like this. It will be a sharp drop to 0, which will approach asymptotically. This is just like that I want to tell you, and now I take another example of similar kind. So I just take another example, and that is the question concerns the moon, and we calculate the value of small g, is acceleration due to gravity of moon on its surface. The data are given here, and all we have to do is to substitute these data in this equation, capital G M moon upon R moon square. Of course we can start with capital G M1 M2 upon R square. Okay, when I substitute these data, then I get this to be equal to 1.64 meter per second square. This was important to show to you that on the surface of the moon, if I have the value of acceleration due to gravity, or the field at the surface of the moon is much less than the field at the surface of the earth. Okay, turns out to be 1.64 meter per second square. Now we take up another example. A body weighs X newtons. It could be 20, 50, any value that can be given numerically to you, on the surface of the earth with a radius r. How much does it weigh at a height over the surface of the earth? Height h is equal to r by 2. So naturally, this is an exercise in the variation of the value of small g, or the value of the field with height. I am just taking this example because the other example that I will take will have a value of h which is not comparable to the value of r, which is very, very small as compared to r. And then there is a formula, and that formula I will talk about in the next outing. So mg, which is the force, is equal to x. weighs. Okay, the weight is equal to x newtons. This I can write it small g into gm upon r square, where gm upon r square is the value of g. So I can write that gm upon r square is equal to x upon m. This is one result that we obtained, which we will use subsequently. At the height h is equal to r by 2, I just write the formula again, f is equal to capital G n m upon r plus r by 2, which is height, squared. Okay, so I just take r out and I get r square here, and 1 plus 1 by 2 whole square. This turns out to be equal to 3 by 2 whole square, which turns out to be equal to 9 upon 4. So capital G m upon r square into 9 by 4. So this is, I write capital G upon r square, I separate, okay, and I get this value as 4 will go up and 9 will remain in the denominator, 4 will go to the numerator. So this becomes equal to, what do we write? Capital G upon m upon r square. I'll just write x upon m from here. Okay, so x upon m into 4 m upon 9. So m and m cancel out. Okay, m and m they cancel out, and we get 4x upon 9 newtons. Why I took this problem as an example is the reason that the height now is, I have made it comparable. You could have a height of r instead of r by 2, and then here I will get r plus r whole square, and this will become equal to 4r square, and we can accordingly find out the value of the weight of the mass at that particular height, or the force which is acting on it at that particular height. Or also I can ask you to calculate the value of the field at that height. So if we have something like a binomial expression, 1 plus say x raised to the power of say minus 2. So if this x is very, very small, this will be equal to 1 minus 2x. In the linear approximation, the binomial approximation, where x is very, very small as compared to 1. Okay. So this kind of an equation we are going to use further in the case of the determination of how the value of g changes with the height above the surface of the earth. We will go deep down into the mines and find that there also the value of g decreases, as also in many other situations, and we will talk about to you. I'm just giving you a thought, what happens if there is a shell where the mass is all along distributed in this shell, okay, and we want to find out what will be the value of the force on mass small m situated inside, as also another mass which is situated outside this shell, thin shell, okay, because a solid sphere we can say that is made up of many concentric shells together, etc. We will talk about these things. Also the gravitational mass and the inertial mass, etc. In the next lecture. So I just like that I am indicating to you about this and about your comments in the comment section of the. Thank you very much.